So let's start. It's great to have Francesco D'Eramo today from Padova, and he will tell us about hot actions.
Okay, thank you, Javi. And first of all, I would like to thank the organizers for giving me this opportunity to present some work I've been doing on the last few years. Of course, as many of the speakers this week, for me, it's the first time I give a talk in person again. So it feels very, very good. Actually, I was in Florence in January 2021, because of the school that was online, but I was organizing from here. And it was a very different Florence. There was nobody in the street. Everything was empty. So in some sense, it was nice, but I think it's good that we are slowly coming back to normal. So can we please remove this Zoom? Yes, if it's possible, it would be better. Thanks. And there are messages in the chat. I don't know. I mean, I can start, and in case it affects, I will. Okay, so the topic of my talk is hot actions. I will explain what I mean by hot in a second for those of you who are not familiar. Of course, the motivation of this effort is the strong CP problem. So our attempt to understand why nature, in particular strong interactions, are invariant under time reversal up to the experimental resolution, of course. And this requires, from the theory point of view, to fine-tune the theta parameter to a very small value. And among several solutions, the most appealing one is the QCD Axion, which arises as a low energy degree of freedom of the Peccei-Quinn Mechanism, named after the two scientists that proposed this mechanism. It's not the only solution, but it's one of the most appealing, if not the most appealing. And broadly speaking, within this framework, there is a new global symmetry, which has two crucial requirements. The first one is that it's spontaneously broken at the scale FA. So in lots of my plots, there will be this scale FA. So FA is the scale of the symmetry breaking, which is much larger than the weak scale, just to give you some reference value. And then this global symmetry must be anomalous under strong interactions. Okay, these are the two crucial requirements. And at the high symmetry breaking scale, here FA, much above the electroweak phase transition, you have this pseudo-Goldstone boson as a consequence of the symmetry breaking, which has this anomalous coupling to the gluons. This is a consequence of the fact that the symmetry is anomalous. Of course, this is not the only coupling of the actions. It depends on the model, but this is the coupling that you need if you want to solve the strong CP problem. And then once you go to low energy, especially around the QCD phase transition, the axion develops a potential. And this potential, here I'm just taking an approximation for the around the minimum can be approximated as an harmonic potential. There is this important variable, which is the axion mass. I will come back to that in a second. But the thing I want to say is that the minimum of this potential is conserving CP. And so the strong CP problem is solved dynamically because the theta parameter gets promoted to a field, the field evolves in the universe, and the expansion of the universe drives the field toward its minimum. Okay, so I mentioned the axion mass. Let me give you some more detail. The axion mass can be computed in terms of the axion decay constant, FA. Here is the result. This number is not something we know, okay? The scale of Peccei-Quinn symmetry breaking. I say that it's much larger than the weak scale. Dark matter gives us a hint that this scale is around this number, okay, with many caveats, but that's one possibility. And so the axion is a very light degree of freedom. Okay, here you see if the decay constant is 10 to the 12th GeV is micro electron volt. Okay, so we have a hypothetical new particle which is very light, and it's also very weakly coupled. Very weakly coupled because all the axion couplings, given its pseudo-Dumble-Goldstone nature, they are suppressed by 1/f. So the axion is very light and is very weakly coupled. So there are two immediate implications of this fact. The first one is that the detection is challenging, okay? It's a very elusive degree of freedom. But there are novel ideas, which I will not talk about in this talk, but it's something that in the last 10 years has been literally blossoming, okay? I will focus on the role of the axion in the early universe, and being so light and so weakly coupled, we will see that there are interesting things happening in the early universe. So in particular in this talk, I will focus on thermal, hot, I will explain what I mean by hot, axions produced in the early universe. Okay, so this is what I will tell you today. So before I talk about hot axion, just one slide, okay, to remind you another important property of the axion, and this is the fact that the axion is a viable dark matter candidate. Okay, so the axion can account for the observed abundance of dark matter, which is another reason why the axion is so appealing. So it solves two problems, two fundamental problems in particle physics. I would like to advertise a talk by Josh tomorrow that will tell us more about the axions as a dark matter candidate. Here I will just show this plot where you have on this axis the axion decay constant at the mass. Remember, they are related. I showed you the equation before. And here is the initial value of the field in the evolution in terms of this theta variable. And this dashed line is when the initial angle is around 1, the initial axion value. Okay, so there are several options for the axion production in the early universe, but as you can see from this plot, if the axion initial value is of order 1, and also once you count the theoretical uncertainty for production of the cold axions via topological defects, that's something we will hear more about tomorrow, this is a preferred range for F, okay? So 10 to the 9, 10 to the 11. There are many, many caveats to this statement, okay? There is nothing wrong with leaving here, okay? This is just to give you a reference value, but it's easy to have viable axion dark matter with F in this large value, okay? Sorry?
Why is wiggly this line?
This line?
Yeah,
Why it's not straight?
Yeah.
It should, I guess it's something with the G star modification of the degrees of freedom. I mean, the scaling, the naive scaling of theta square times F to a given power is assuming doing this semi-analytical. If you do the numerical treatment, but it's almost straight, you see. Okay, I guess that's the reason. Okay, so now the subject of today's talk, hot axions. So what are hot axions? So hot axions are axions produced by collisions of thermal bath particles, so even decays, okay? So we start our universe after inflation, we do the reheating. Let's assume there are no axions producing the reheating, which is an assumption. Then we can still produce axions from these processes in the early universe. And of course, these B particles are bath particles, so these are standard model particles, and they have a mass much, much larger than the mass, okay? So the typical kinetic energy of the axion in the it is quite large, is much higher than the axion mass. So that's what I mean by these particles are produced than their mass. So they are very relativistic. And this process may be efficient or not. They may thermalize or not. That depends. Okay, it's something you have to check. And eventually, they decouple from the thermal bath after they are produced, and they free stream. And they free stream in a way we understand. So in particular, at the time of CMB formation, they are still relativistic. Remember that the temperature of CMB formation is 1/3 of an electron volt. Okay, that's the scale of CMB formation. And the axion is much higher than the lateral wall scale, if you remember the equation I gave you before, okay? So the way to unveil the presence of these hot axions is by looking at this parameter that for historical reason is introduced once we measure the radiation budget in the CMB spectrum, which is delta N effective. It's the number of additional neutrino species. It's something that it's introduced conventionally, but it doesn't stand only for neutrinos. Anything which is contributing to radiation will contribute to delta effect. Okay, so this is a way. For now, the Planck bound is consistent with the standard model contribution, which is this N effective is a bit more than 3. Okay, it's 3.044, I think, because neutrino decoupling is not instantaneous. But in case there is a detection, then we can compare with any given axion model if we are able to do the calculation for the abundance of these axions. If even if there is no detection, we can use this observable to put bounds on axion models, okay? Because these are just testing particle coupling of the axion with standard model particles, okay? So how well can the experiment check this effect? Okay, we always have to check with the experimental resolution. So this is a plot that we did with the two postdocs in Padova. There are other versions in the literature of this plot. We made our own. So this is the contribution of delta N effective from relativistic particles that was once in equilibrium with the standard model bus, and it decoupled at the temperature TD, okay? And so different colors mean different species. It's just the degeneracy factor, okay? If you have a Weil fermion or Dirac fermion, you have 2 or 4. You have 7, 8 for the Fermi-Dirac statistics. So that's the only difference among these lines, okay? But the feature you see in this plot is that the later you decoupled, so smaller temperature, the larger the effect is. And this is, of course, a consequence that the standard model bus has less degree of freedom if you go to later times, okay? So let's see what the experiments are doing. So at the moment, Planck is ruling out hot particles that decouple around the QCD phase transition, okay? These are the 1 sigma and 2 sigma discovery reach for a future CMB stage 4, okay? Which is, I mean, this is not a coincidence, like the target of this service is to probe relics that decoupled above the electroweak phase transition, and this green line is a scalar particle with 1 internal degrees of freedom. So this is the case of the axion, okay? So you see, we already know something, but in the next decades, we are going to explore this region much deeper, okay? So this is more general. It's not only about the axions, but I want to discuss what we can learn about axions from this data. Question?
Is your axion also dark matter, or is that not like going to be dark matter, or is that not a demand?
So it depends, because it depends on the value of f. So I will show you plots of f within a given model, and then you can compute the relic density and see what but these are two separate contributions. But it is possible that you both have a signal in the CMB and at the same time you have dark matter.
I was mostly wondering because I was like, if it's not dark matter, then presumably you have some other sector that gives you dark matter, and then what if that sector also, you know, relates to the axion somehow, like, because you're just looking like at stuff that came from the standard model decay, right?
Yes. Yes.
So would you expect that to significantly affect things if the dark matter also, let's say, interacts via the axion portal or something? I don't know.
I mean, you mean if you have dark matter coming from something else?
I mean, yeah, dark matter coming from something else and then decaying to the axion, that's modifying.
Yeah, I mean, I will discuss, that will be clear in a second, but okay. I'm discussing within a specific axion model, I'm computing the contribution to delta N effective. Of course, if you add more stuff, then that can be affected.
Thanks.
Within a given model, I'm doing the calculation. Okay. Okay, so how do we compute this abundance? So this plot is a bit rough because it's assuming thermalization, okay, which is not always the case. You can produce axions and they may never thermalize, but still be around. And also, if we focus on axion that decouple below the weak scale, then you see that this contribution is growing up quickly. Okay, so the way the decoupling temperature is usually computed is by imposing gamma equal h, the interaction rate equal to the expansion rate. And this is a bit, it's good to get the order of magnitude estimate for the temperature, but you see that here, even a factor of 2 or 3 in the temperature may change the contribution. So we want to do a good job, and we want to compute properly how many axions we produce. So the tool is to solve the Boltzmann equation. The left-hand side is the usual one. Okay, it's the geometry of the expanding universe. The right-hand side is accounting for the interactions. So this sum over gamma alpha is the sum over all possible processes producing the axion or changing the axion number, and we sum over all of them, okay? And then once we solve the Boltzmann equation, we end up with a constant NA over S, which is the axion comoving density. And then the mapping between the asymptotic comoving density and delta N effective is trivial, okay? So that's what we are going to do. And of course, as already somebody asked, and as I wanted to say, the calculation depends on the axion model, okay? So broadly speaking, the axion has 2 types of couplings to standard model particles, okay? Look at this plot. I want to discuss late production of the axion, because if the axion are produced here, by here I mean outside of my slide, then the contribution is very small to delta N effect, is barely within reach of CMB surveys. So I want to discuss production standard model particles, and there are these 2 classes of couplings. There are gauge bosons and there are fermions, okay? And within a given axion model, we know these coefficients. The only model independent one is the one to gluons, if we want these axions to solve this. I should say that these calculations can also be employed for generic ALPS, okay? As long as they're light, as long as they are relativistic at the CMB formation, they give you a constraint from delta N effective. But I want to focus on the QCD axion here. So the gluon coupling is always there, okay? Okay, so this is the plan of what I want to tell you today. First, I will discuss production through leptons, axion coupling to leptons, then axion coupling to heavy quarks. The reason why I do not discuss light quarks is that light quark coupling then they bring additional complications, because then we have to discuss what happens around the QCD phase transition, okay? Because as we'll discuss, this quark scattering is dominated at the quark mass, when the temperature is equal to the quark mass. I will show you why. And so if you consider, for example, the charm or the strange, then you cannot just do a perturbative calculation and apply the Boltzmann equation the way we compute the Rayleigh density for WIMPs, for example. Okay, so here is the next subject, how to compute axion production around the QCD phase transition, which is something that we completed this summer in this first paper. And then I will discuss specific axion models. So I would like to break, besides following the timeline of the papers, it's also good to discuss different cases at a time, so we can see how things get more complicated as we consider different couplings. Of course, this is the most interesting part, because in the end, I'm interested in computing the axion abundance within a given UV, okay? But so let's start from the case from leptons. Here I have mu and tau. I do not have the electron. The reason why I do not have the electron is that the axion coupling to electron is severely constrained by stellar physics. And it's so constrained that basically we never produce an amount of dark radiation that can be detected. Okay, so the axion electron is not interesting. Well, it's not interesting. It gives you nothing you can see. Okay. Okay, so once we, I mean, of course, we did everything numerically. We solved the Boltzmann equation. We did the plot. I will show you our plot evaluated through a numerical analysis. But just to give you the scaling of the rates with the fundamental parameters, the key quantity to compute is this ratio between gamma and H, the Hubble expansion rate. Gamma is the interaction rate. And for this talk, which is also what we did in our papers, I'm assuming a standard cosmological history. Okay, so at the time of axion production, the universe was dominated by radiation bath made of standard model particles, the usual way. Okay, so here I know that Hubble goes like T square of m and Planck. In particular, this exponent Q is important, okay, because when I compare the Hubble rate with the interaction rate, if the interaction rate scales with the power higher than 2, it means that my production is UV sensitive. If the production scales with an exponent less than 2, then it's IR sensitive, okay? So this tells me when production is mostly efficient and where should I look at, okay? Okay, so coming back to leptons. In the phase where the electroweak symmetry is unbroken, the production rate is controlled by this type of scatterings, okay, where H is the X doublet, okay, L is the lepton doublet, E is the right-handed lepton singlet, and you have, of course, all the processes that you get through crossing symmetries, okay? This is just one for illustration. There is a simple way to see this. If you remember, the axion was coupling through the derivative to the axial current of fermions. You can just integrate by parts, apply the equation of motion. You see that you couple the axion to the Yukawa operator. So this is just a Yukawa interaction of the standard model. The rate for this process scales like T cube divided by FA squared. So all the rates in my talk will be like FA to the minus 2, okay? Because the axion couples with the, there is also one axion in the final state. Each vertex brings an inverse power of FA. So all the rate scales like FA to the minus 2. The T cube comes from dimensional analysis, and the Yukawa coupling of the lepton is just a consequence of the vertex here, okay? Below the electroweak phase transition, the production is given by this lepton and anti-lepton annihilation to photons and axions and all the other diagrams that you obtain by crossing symmetry. In this case, there is a chirality flip necessary in the diagram that brings in the amplitude an additional power of the lepton mass, okay? So if you have an additional power of the lepton mass in the amplitude, you have that the rate goes like m squared. And so by dimensional analysis, you can find the power of T. This is the first power. So you see here you have T cube, here you have T. Okay, so as I said, this has to be compared with the Hubble rate, okay? So in the case where you are in the unbroken phase, the production is UV sensitive, okay? The higher the temperature, the more efficient you are in producing axions. So in particular, you will be maximum at Curie heat. Once you are below the electroweak phase transition, this production is infrared dominated because it goes with the first power of T, okay? So in this case, when you go to lower temperature, the production will be more and more efficient, of course, until you get to the lepton mass. At that point, there are no more leptons in the thermal bath, and you stop being efficient. So it's more interesting to focus in this region, below the electroweak phase transition, because, okay, above can be efficient, but if you produce them way above the weak scale, the contribution is barely within the reach of CMB service. If you go below, there is a potential large contribution to delta and effective, which is what we want to compute, okay? So you see, I reproduce the scaling here again. Oh, sorry, yes.
I have a couple of questions. So first of all, the second process is like important to consider thermal effects because
Which one? Which one?
For this one with the plasma, for example, with the photons, right? You're considering temperature below the electroweak phase transition down to the electron mass. I would expect, so did you take into account thermal correction to the photons?
So for this process here, they are not relevant thermal correction. You have no singularities. There is an exception, the gluon scattering, which I will discuss, where thermal correction are crucial. For this case here, no.
They're not relevant.
There is no reason to worry about it.
And then another question is about stellar constraint. You mentioned that for electron, like you are killed, and for muons you are not, right?
Yes.
But if I think about, like, for example, horizontal branch constraint on electron coupling and supernova constraint on muon coupling, they're not like super different, right? So did you consider?
So for the muon, I will show you in the plot. There is a bound on the muon. It's constrained. I will show you in a second. So we accounted for the constraint from the supernova.
Okay.
But you know, the paper is from 3 years ago, so it may be not updated to the recent ones. Questions? More questions? Okay. Okay. So summarizing, if you look at these rates, so the production rate is enhanced for Levy leptons. You see that it goes like the Yukawa or the mass. So gamma is larger for heavy leptons. At the same time, going to lighter leptons is convenient because you may keep the axion in equilibrium until the lepton mass, until when the temperature is around the lepton mass, and so there would be a higher contribution to delta N-effective. Remember that the lighter you decouple, the bigger the contribution is. So here is the result. So you see, okay, sorry, here I think the muon bound is around here, 10 to the 6, if I remember correctly. But let me explain this plot, which will be similar to other ones I will show. You have delta N effective divided by F over C, where C is the dimensionless coefficient in front of the axion coupling. Okay, so we have three cases: muon scattering, tau scattering, and tau decay. In particular, we consider off-diagonal tau couplings going to muon axion. Okay, muon off-diagonal couplings are excluded because you have muon going to electron plus axion, and again, the searches are very severe. So you see that in this case, if you only focus on the Kelvin to leptons, you are able to produce delta N effective rather large, but you need a rather small value of the axion decay constant. Unless these dimensionless couplings see, there is a hierarchy. So here we focus only on the coupling to leptons, but it's clear that once you embed in a UV complete model, as I will do in the end of this talk, then this production is not very efficient. Just for fun, since it was 3 years ago, we also tried to see if the muon, the axion coming from these processes could account for the famous Hubble tension. You know, delta N effective is one way to reconcile this discrepancy between early and late time measurements of the axion of the Hubble constant. And then we did a careful analysis of the data from Planck, but the short message is that maybe you go from 4 sigma to 2 sigma, but the tension remains, and you have to live with this very strange parameter space region where F is of the order of 10 to the 6. Okay, questions? Microphone, wait.
What is the mass of the axion typically, for example, for a small value of F?
The mass here. So, I mean, this is F over C. Okay, so the problem is decoupled. If you assume a C of order 1, C is the dimensionless coefficient in front of the axion coupling. Okay. If you assume a C of order 1, the mass of the axion is large. It's large to the point that you may wonder if they're still relativistic at the CMB. Yeah. But of course, this is a separate question. I mean, the axion mass is set by the coupling to gluons.
Okay.
Fate il microfono over.
Francesco, is it important the production via the photon coupling? The production of action via the photon coupling?
No, I mean, it's not, it's suppressed with respect to this one. I have a plot later.
Always photon.
There are always photons, yes. But what do you mean by photon? I'm assuming only this vertex in this case.
Yeah, but in general, if you have a QCD action, you have also.
Yes, but I will discuss UV completion later. Here, I was focusing only on the production driven by this coupling. Okay. But in a UV completion, there are coupling to photons, but then you also, I mean, the one to gluons win because they have the same scaling with the temperature, but the strong coupling constant is bigger. Okay. So Hubble tension, maybe, but not so much. Okay. Okay, heavy quarks. So heavy quarks, I will be fast here because the discussion is identical to the case of leptons. The only difference is that you can have gluons in the final state, okay, before I had photons. And so the scaling is the same. The only non-trivial things when you discuss heavy quarks is what happens around the electron weak phase transition, because the top mass is right there, okay? So to have a smooth treatment of the production, and in particular, a smooth result for the rate, you need to do a matching, okay, across the electron weak phase transition. For the leptons, all masses were below, so you could work in the broken phase. For the top, you have to be more careful. So that's what we did in the paper that we finished last December. And as I mentioned already, you can only do a perturbative analysis for bottom and top quark, okay? because this axion production via quarks is infrared dominated. So if you couple to the charm, you are dominating the production around the charm mass. Okay, so these 3-level cross sections is not something you can employ clearly. I will get back to that in a sec. Okay, so here we have again the result of delta and effective versus FA with the. This is the case of top coupling. We set the top coupling, the dimensionless coupling, to 1. And you see that we consider different processes above and below. So in particular, you have scattering with the weak gauge bosons below. Above, we are scattering with the Goldstones. We match the rates. Of course, everything worked perfectly. And we have a smooth prediction for delta and effect as a function of S. Okay. And here also for the B. Okay, now, I told you about leptons. I told you about bottom and top. Please, yes.
Just a brief question, maybe you said it, but why didn't you show all the decay processes for the top?
Decay processes. Oh, we did in, sorry, good question. We did in this paper. I didn't put in the slides because I have a finite amount of time. But we did. I will come back to flavor violation in the end about some more work in progress. I have the last slide will be on that.
All right.
But this paper has a more accurate analysis also about the decay.
Thank you.
Thanks for reminding me. Sorry, I forgot. Okay. QCD phase transition. Okay, so now let's. I mean, the final goal is to produce a prediction for delta and effective as a function of F for a given UV completion. Okay, not just for a single coupling. So we have to deal with this coupling to gluons. Okay, and this coupling to gluons is something that you have in every axion model. Okay, every axion model has this coupling. And it was well studied above the QCD phase transition and below the QCD phase transition. By above, I mean also above the weak scale. Okay, very, very high temperature. It was studied the effect of these scatterings in this paper. In particular, this last one by Salvio, Strumia, and Exue was the ultimate result about axion production by the gluon operator for temperature above the weak scale. Okay, below the QCD phase transition, we had pion scatterings. Okay, that was studied for the first time in the 90s, and there was a more recent paper this January, where they also showed that this production can be computed within the current perturbation theory framework only for temperature below 60 MeV, roughly speaking. The reason is that above this temperature, NLO corrections become as important as the leading order result. Okay, so here is the paper from 2013 I was referring to, and you see, Paolo asked about the photon coupling. So here we are in the unbroken phase. So you have GY, the hypercharged boson, but it's the same. You see that on the vertical axis you have the production rate. And the production rate with some normalization that makes a lot of sense. In particular, you have FA squared because the rate scales like 1 over FA squared. You also have temperature to the 6. Okay. And then there is this function that has not a very strong dependence with the temperature. This red line, the solid red line, is the updated result. Okay, G3 is the contribution from gluon scattering. And the green line and the blue line are the electroweak gauge boson. So you see this is much suppressed with respect to the other one. So if you have a given model, the gluon coupling will win. What I want to emphasize about this plot is that the horizontal axis here, you see that two things I want to say about this plot. Okay, this plot is correct, but I want to say two things. One is that the temperature in the horizontal axis goes only to low values as low as 10 to the 4 GeV. We are still above the electroweak phase transition. If we want to have a smooth treatment of the QCD phase transition, we cannot use this result. We are way above the QCD phase transition, okay? That's the first comment. The second comment is that this vertical axis goes up to 10 to 12 GeV. And of course, this assumes that the dimension 5 operator with the gluon is local all the way up to temperature of 10 to the 12 GeV. But we know that this is the result of integrating out some color fermion, which are responsible for the anomaly. in the case of the DFS axion, which I will discuss at the end, the first color PQ fermion is the top. Okay, so this result doesn't apply to the DFSZ axion. If you have the KSVZ, you have this heavy fermion that carries the anomaly, color fermion. The mass is a free parameter, but at some point it must break this plot. Okay, so once we discuss UV completion, we will keep this into account as well. Okay, so now here is one of the results that we got this summer about the rate across the QCD phase transition. Okay, so here it's a plot where I'm just setting the stage for the result. Okay, so there is the rate on the vertical axis, and the horizontal axis, I have the temperature. And you see that now the values are around the QCD phase transition. Okay. So the first thing we do is that we extended the calculation of thermal gluon scattering all the way to few GV. Okay, all the way to values where you can still use perturbation theory. Of course, you have to extend the thermal treatment that was done 8 years ago by adding many things. For example, the fact that the quarks are massive. Okay, so you have quarks that decoupled eventually in your calculation. Then we did the same. Actually, here the result was known, but the new ingredient that we put into this discussion is this result by Di Luzio, Martinelli, and Piazza from a few months ago. And in particular, the fact that the leading order result is valid only around this value of the temperature, okay? And then there is a gap to fill in between, okay? So in between, we interpolated the result. And of course, I don't want to claim that this is the final result. If you want, I have some backup slides where we discuss also how sensitive is the final prediction on this interpolation, okay? But I want to say a few things. Of course, there are QCD resonances here. There are lots of things, but eventually the rate that you compute is the thermal average of all the scattering processes happening, okay? So the effect of these resonances in some sense is smoothed out by the thermal average that you take. And also the prediction for N effective is integrating this rate across the expansion history of the universe, okay? If you want, we can discuss more about this, but I don't want to tell you that we did more than we did. We just approached the QCD phase transition from both sides, and we interpolated the result in between, okay? We did this for the gluon coupling, but of course, if the axion couples to gluon and quarks, as it is the case in many models, this procedure can be implemented as well, and we did according to the model we were considering. So
what is the region that dominates?
It depends. The abundance, it depends on the value of f. So this is the rate normalized by f squared. So the lower the f is, and the lower you go here, of course. But the question, I mean, this is the rate normalized in a way that allows you to plot the result independently on f. But then to identify where production, you need to specify f. It could be, yes, it could be here, it could be here. I have a backup slide that we can discuss about this. Okay, so to conclude in the last 10 minutes, I have just two famous UV completion, the usual one, the KSVZ, the DFS. Now we have a UV complete axion models. You have a finite amount of parameters. You have the axion coupled to all the thermal baths. We did a calculation for delta N effective, and we gave predictions as a function of the axion decay constant. So the first one is the so-called KSVZ axion. Okay, so here are the Lagrangians, 3 Lagrangians. Okay, in the UV, this is the renormalizable theory where you have a new complex scalar and a new fermion colored that is responsible for the anomaly. And there is a potential which has a Peccei-Quinn breaking minimum. So below the Peccei-Quinn breaking scale, you have the axion A, okay? I still keep psi in the spectrum, okay? And the mass of psi is a model-dependent parameter. And the axion couples to psi through this interaction where if you expand exponential to the first order, you have a Yukawa interaction between the axion, pseudo Yukawa actually, the axion and the psi. And then you go below, and below the finally below the mass of psi, you generate this dimension 5 operator with the gluons. Okay, above the mass of psi, you have no operator with the gluon. Okay, so here is the result for the rate. Here now you see the temperature goes across many orders of magnitude, and on the vertical axis you have gamma normalized by F in the way I was discussing. And this vertical green line, M psi, is the mass of the fermion psi, which is a free parameter we set here to 10 to the 5 for illustration, okay? For illustration. Actually, in the end, once we discuss the predictions for delta and effective, the specific mass of psi, I mean, this psi has color, okay? So it cannot be too light. It has to be above the TV scale. And so the impact of this value to the predicted amount of delta and effective is not actually so important. Okay, oops. So I want to emphasize that above the fermion mass, this rate goes like 2 to the 4th, and below like t to the 6th, okay? In the previous plot, the paper by Salvio, Strumi, and Xue, it was t to the 6th all the way up to 10 to the 12th, but actually you have to account for this threshold. Above, this is not the case. For the KSVZ, it will be even lower. It will be at the weak scale, the difference. Okay, so here is the first result for UV completion. So let me discuss this plot. We have delta and effective on the vertical axis as a function of FA, the axion decay constant. In the KSVZ theory, FA is the only free parameter, okay? Well, we set the mass of this fermion to 10 to the 5, but as I said, it's not actually so important, okay? So as a function of FA or the axion mass, we put both, okay? On the two horizontal axes, we can predict the amount of delta and effective. So we produce this plot by running the Boltzmann equation from some temperature Ti, which we set to different values, and the temperature Ti is the moment where we assume that there was no axion abundance, okay? This is, of course, something that can be different if you're heating, okay? We only consider production through this scattering from thermal bath particles. If you're reheating, then you have more, okay? So this is the minimum amount you expect. You can see that in that way. And you see, if this Ti is larger than the fermion mass, then the prediction is insensitive on Ti, okay? The reason is that if you start above the fermion mass, everything is normalizable. The coupling producing the axion are all normalizable, so you have IR sensitivity, and it doesn't matter where you start, okay? So I would like to focus on this red line. And you see that at the moment, Planck is far from testing the delta and effecting arising from this from the KSVZ axion. So you see, this is the Planck line, okay, the exclusion bound by Planck. But you see that CMB stage 4 surveys will test a region which is not yet excluded by stellar bound, which is this vertical gray region. And you will go to values of F, coming back to your Itai, to your question. You see, here you can have dark matter, okay? And you can also have a signal in the CMB, okay? Okay, so for the DFS, the story is very similar. You have, in this case, you do not have new color fermion. So the color fermion carry Peccei-Quinn symmetry are the standard model quarks. You have a 2x doublet model with some potential interaction. And then eventually you couple, in this case, you have a richer structure of coupling. You also couple to quark, you couple to leptons for the rate. This is important. And so we accounted for all the possible couplings. The parameters to fix here are the mass. So we decouple the heavy X doublet, okay, just for illustration. The heavy Higgses, we set them to 10 to the 100 TeV, okay, this scale here. There is another parameter which is tangent beta, the ratio between the two X webs. As you see, putting tan beta equal 10 or 3 doesn't change the rate by much, and it only affects the rate above the lateral wave phase transition. So here you have a richer set of options for the rate, because you start in the UV where the rate actually goes like T to the second power, because the coupling of the axion to the Higgs is relevant. Okay, it's not marginal as it was before. Okay, so you have dimensional analysis gives you Q less powers of T. Then below the mass of these heavy Higgses, you have T to the 6, which are the dimension 5 operators coupling the axion to the top and bottom. Depending on tan beta, you have different dominations, but here the production is driven by top and bottom quarks. Here the same, but the chirality flip gives you a different behavior with the temperature. Here you have T to the 4th. And unlike the previous case, you also have a rate below the pion mass because you couple to the leptons, okay? And so you have again this T to the 4th behavior because you couple to the leptons. Okay, so here is the plot for the DFS. So this is similar to the one I showed you before. TI is the same, so I will not repeat everything, okay? It's the same. The only difference is that now we have stronger stellar constraints because of the coupling to the electron. In this case, that was not present in the KSVZ axion. And so you see that you can still reach a region of F which gives you enough dark radiation to be detectable, and also axion dark matter in this lower end of the range. But the parameter space you explore for the DFS is smaller, okay?
Yeah, I have one question.
Yes.
So I guess you don't expect that the stellar bounds are going to be improving by the time CMBS4.
Yes.
Is that the case?
Well, as far as I remember, I do not think they will get here. So they will not improve by the factor to cover this region, but I'm not 100% sure. Okay, so that's a good point. That's a good point. But anyway, so I mean, the stellar bounds have many caveats, so in the end, it's good. But that's true. That's true. Okay, so I came to the conclusions, and well, I just discussed about the right part of this plot. The axion, of course, is famous for solving the strong CP problem, for providing us with a good and viable dark matter candidate, is the target of many experimental searches, but it can also give signals in the CMB, okay, through an additional amount of relativistic degrees of freedom, which, of course, detecting a delta and effective from the CMB will not point to axions, but it's something that once you have a given model, you can cross-check and you can use the CMB data to put bounds on the axion. The last thing I would like to advertise, which is this plot here. Somebody asked me before about the top level violation. We did that, but something we are doing now with Seokun Yoon, one of the two postdocs that did the other papers with me. He will be here for the next few weeks, I believe, if I remember correctly. So you can ask him more about this work that we are finishing right now. But the message here, you have the off-diagonal coupling of the axion between the bottom and the down quark and the bottom and the strange. Bottom line message is that at this moment, there is a lot of interest in flavor axion violating couplings. There are bounds from current experiments, bound from future experiments. Here you see these continuous and dashed lines. At the moment, Planck is far from testing this region, but something complementary about axion flavor violation that we will reach in the next decades is also from this CMB stage 4 surveys. You see, for example, here for the coupling bottom to the down quark, you see that this is the prediction for delta and effective, and in principle, you can exclude regions that they're not excluded by now, but also future experiments will be there. And so you have an interesting interplay between flavor physics and cosmology. So we'll stop here, and I'm happy to take more questions. Thanks.
Thank you very much, Francesco. First, if there are questions from Zoom, which There is one. Please go ahead.
Thank you. Hello. So I wanted to ask about this production from leptons, because you said it's the dominant one below electroweak phase transition. So so you mentioned something that that is important until the lepton mass, right?
Sorry, if I understood correctly, what you asked
about
this.
Yeah, one
lepton?
slide before, yes.
Here?
Yes, exactly.
Okay.
So below electroweak phase transition, right? So it's basically the lepton scattering is important, you know, as long as the leptons are present in the thermal bath, right?
Yes.
So and maybe I misunderstood, but I thought that you mentioned that, so you basically you know, integrate the Boltzmann equation until the lepton mass or the decoupling temperature of a given lepton, because it's not really the same, right?
Okay, so I think I understood. So let me answer, and then you will tell me if I answered the right question.
Okay.
So what we did, let's take, for example, the muon mass, okay? The muon production driven by muon. We integrated the Boltzmann equation from temperature much above the muon mass, and we continued several orders of magnitude below the muon mass. So the Maxwell-Boltzmann suppression took care of everything I said. At the moment you go below the muon mass, the muons disappear from the bath, and then this is accounted for in our numerical analysis. Was that the question?
Yes, yes. So basically you also solved the Boltzmann equation for muons, right? Or
Yes, yes. So we solved the, so I mean, to produce these plots here, we solved the Boltzmann equation. Let's take the blue line. Muon, yes. We went to temperature from, I don't know, 100 GV to 1 MeV, okay? So the muon was disappear from the, at some point you see that the comoving axion density reaches a constant value.
Okay, okay. Okay, that's also my question. Thanks.
Okay, thanks.
Thank you. Any more questions from Zoom? I guess not. And there were here some.
Can you go back to the plot where you have the production rate as function of the temperature? I think for the
Which one?
For the second action model, DF.
Yes. Here. Why not? Okay.
Yeah, right. So just by looking at, let's say, naive scaling, where I divide the rate by the Hubble, I will guess that most of the production occurs around the mass.
Yeah. Sorry. Okay. So this rate gamma that I plot, I should have said that. I apologize. This rate gamma is the one appearing on the right-hand side of the Boltzmann equation. So it's something with mass dimension 4. So it's the number density of the bath times the rate that you probably were referring to. So you have to, you have to divide by T cube all of these numbers that I gave you, and then thanks. Okay. Yes.
Are there more questions?
So here in your EFT, in the, for instance, KSVZ model, you have assumed you have the radial mode, for instance.
Sorry, what model?
KSVZ.
Okay.
You have integrated. What happens if the radial mode is light?
Oh, the radial mode. Or the
yes.
radial mode.
What happens if it's light? Can it open a new production channel?
Well, I mean, if the radial mode is lighter, then you also have production driven by these scatterings with the radial mode. Okay, so, but I mean, as what I try to say is that everything that happens above the electroweak phase transition, imagine you have a radial mode very light, okay? Light, I mean TV scale. They produce, even if they are successful to thermalize, they give you a delta effective of 3%. Which is really, really small, okay? So in the end, the numerical analysis will be different if you also have the radial mode in the game. but the plots like this will be not affected by much, because these results are controlled by production later than the electroweak phase transition. Okay, so unless you have radial mode, which is very, very light, but then, I mean, okay, if you have the radial mode, it's straightforward. You just add other processes to produce the axion. But I mean, unless it's below the TV scale, nothing changes from the practical point of view.
What would be the Feynman?
Well, I mean, you have the coupling between the Goldstone boson and the radial mode. So you just need to expand the Lagrange and then you find all the vertices, but it's interactions among scalars. At the minimum, you have those, right? Yeah, the microphone. Okay.
Anyone else? Okay, if not, let's thank Francesco again.
Thanks.